I wasn't quite sure about following Randy, partially because he's a hard act to follow, but I also wasn't sure how well our talks mesh. But Randy was talking about something that he addressed in theory a few years back, and now he has the data to back up what he was talking about. And I'm going to do the same thing. I've been fighting my boat electrofishing effort battle for several years now, and previously I was really doing it more from a theoretical standpoint. But we've spent the last 3 years gathering data for that, and now I can actually present some results. I'm going to start with the acknowledgments, so I don't have to worry about that at the end. As with anything that involves long-running annual sampling, there's a lot of people involved, more than are on this list. But I especially want to thank these folks who went out there night and day, who kind of helped me as these ideas were evolving, think through this stuff. I said I was going to talk data. I'm actually going to start a little bit with theory, but I promise we'll get there to real figures. Electrofishing is a survey of space. So we are moving through an area and seeing what fish are there. The majority of the fish we catch with a boat electrofisher are the ones that are present at the instant the field passes them. Something like this, my fancy animation here. Electrofishing is not a survey of time. This isn't like a gill net. We can't sit there in the middle of the lake and wait for the fish to come to us. It doesn't work that way. You might get a few, they might happen through there, but you're running lights, you're running a generator. They are not attracted to you, except for weird little fish like maybe gobies. But for the most part, you have to be moving. We are surveying space. By and large, though, we measure electrofishing with time. So we do it with seconds of electricity applied. Or we say we're going to do a 15-minute survey, a 30-minute survey. We're using time as a proxy for space. And that works. That's how we think about driving directions. You go 60 miles an hour for an hour, you know how far you've gone. But, well, so that works. But space has traditionally also been hard to measure. This is from Reynolds, 1983. 35 years ago, they recognized that distance and time were both important, and that one of them might be more predictive of catch than the other. However, Reynolds also says that distance is extremely difficult, because back in 1983, you were pacing the shoreline, maybe you were squinting at a hand-drawn map, and let me tell you, I put those maps into GIS, they don't quite fit the real world. Maybe you were actually surveying it. That's really labor-intensive. So we defaulted to time. Why should we be thinking that maybe this isn't the right way to go? Well, time as a proxy for distance only works if you're keeping your speed constant. If you are surveying the lake the same way each time, or if between waters you are keeping your speed the same. Most guidelines talk about this. They stress that you should do it. I think DEC is talking about like 1 kilometer per hour or 1 mile per hour, one of those. But the problem is that netting fish also takes time. We know that if you move too fast, you miss fish. That's why we say you have to go slow. But we also know that if you move too slowly, you never get anything done. Or at the very least, you lose your crew because they don't want to spend 40 hours on the same lake. The problem is, you have to choose your speed to account for a density of fish that may change. You have to choose this ahead of time. You have to have some boring moments if you're going to use constant speed. Or in reality, you cheat a bit. You say, well, there's not many fish here, we can go a little faster on this lake. But, like I said, this was a survey of space. The two lakes are then not comparable because you're not surveying the same amount of area. You say you do a 15-minute survey, when the time is up, you stop. That's great, but you could cover twice the distance in a low-density lake in 15 minutes. They're not the same thing. And what this really gets at is an idea known as gear saturation. So this is the original Baranov catch equation. This is what's behind all of our ideas of using indices of abundance. Catch, do this here. Catch equals catchability times effort times the true number of fish out there. And catchability is kind of a funny idea, but what it is it's the probability that each individual fish is caught in each individual unit of effort. We can put effort under catch here, take it out of here, simple algebra, and this C over E is catch per unit effort. This is what we're all talking about. You don't need to know Q. You don't need to know catchability. You do need to know that it stays constant. If your catchability is the same, then any changes in this reflect changes in N. It's the whole idea. Problems occur when changes in catch change catchability. So this is no longer constant. And that's gear saturation. What does this look like? Well, this highly idealized gill net is showing fish that are caught here. They're wiggling around. They're probably scaring off other fish. They're taking up space. I said this is idealized. In reality, these fish are probably rolling. They're hopelessly tangling the net. You're never going to get that net back. It's a huge mess. This net is not as effective as it was before there were 3 fish in it. To a certain degree, that doesn't matter much. You've got a lot of gill net. You catch a few fish. Doesn't really change it too much. But there are other situations. This guy's pretty happy. He's got something there. What are the chances that he's going to catch another fish on this line before he lands this one? They're almost nil, right? I mean, unless it's some sort of freak scenario where he gets a much larger fish. But in reality, that never happens. Say it takes him 15 minutes to land the fish. We're measuring effort in hours here. Well, if there are 2 fish out there, he'll be able to catch them both in that hour. If there are 4 fish and things are perfect, he'll have a CPUE of 4. If there are 100 fish, he's going to catch 4. If there are 1,000 fish, he's going to catch 4. Catchability is changing, and that screws everything up. Now, with electrofishing, it's really simple to think about this for missing fish. You go too fast, you can't net them all, they zip by the boat, they're gone. You didn't see them. But you can also slow down, and that's increasing your effort, and that has the same effect. You are saturating your gear. You're saturating your netters. And when you slow down so that they can deal with that, the whole idea of a relative index of abundance is going out the window. So, okay, enough about the theory. What do we actually do? Well, we have these annual electrofishing samples that we do up in the Adirondacks on a couple of lakes. And we used our traditional time fished. So we've been using the counter on our Smith root box. We also added in shoreline distance. And then we had the actual area fished. So put together a device that interfaces the electrofisher, takes GPS points while we're shocking. Those points turn into paths. We can estimate how large the field is on our boat, and so we can buffer that path. And we have the actual area of the lake we fish, which is pretty cool. And in total, we had 288 site survey combinations. So our lakes are broken up into sites from very specific shoreline points that we fish the same way every year. We had nighttime fishing, we had daytime fishing to target bass. There's a wide range of different combinations here. This is a picture of shoreline length. So this dashed line here, this is taken from the National Hydrography data set, would be length for this site. And then this is what that aerial measurement I showed you. So we use pole-ins to lake because our lakes have a lot of coarse woody debris. They've got some really complex topography. It doesn't matter in practice for evaluating this. You can see though we have the exact spots we fished. And we compared these to each other. So we took the catch rates from these. Turns out you get 3 pairwise combinations out of these 3. And we fit models to those comparisons. A simple linear model, a linear by habitat. So is the habitat you're in affecting that? Pretty simple habitat groups, rock, silt, coarse woody debris. And then an asymptotic model. This is what we got. So for these first 2 here, you have catch over time. on the side, and then you have catch over shoreline distance, catch over true area, and then this is shoreline distance versus area. And what you can see is we don't have a linear relationship here or here. Time is leveling out. That asymptotic model fit much better than a linear one did. Whereas over here, the linear model, and actually linear by habitat, it turns out area fished correlates really well with the habitat you're in the shoreline. But we didn't get this here. Here is the obligatory giant table. Really, I just wanted to show you AIC values. Best model, best model, best model, not asymptotic in this one. So what does this mean? Well, that asymptote is the saturation point for a time-based catch rate. And in this case, we got it around 15 fish per minute. That means that on average, our netters couldn't deal with more than a fish every 4 seconds, or since we had 2 netters, a fish every 8 seconds. And if you've ever electrofished, that kind of makes sense. Sometimes you get a whole school of minnows, you can get a bunch of them at once. Sometimes you got a giant bass deep in woody debris, it's going to take you a lot longer than 8 seconds to get it. But you can't net more fish than this on average. It's just simply your time-based effort maxes out there. Of course, we could go slower. You could plan your survey so that you have a very slow forward speed. Well, we also know how density affected this because we had our true area fished. And it turns out that for us, you'd have to be right around 0.13 kilometers per hour. On our smallest lake, and that's not a very large lake, that means to fish the entire shoreline, it would take us 39 hours. That would suck. We're not going to do that. In practice, we've been speeding up, slowing down, dealing with those density changes. And I think honestly that's what most people do. But like I said, that screws everything up. Okay, so is this just us? Well, last year a group from Ohio DNR published a study where they were looking at catchability, and they compared fish per hour versus fish per kilometer shoreline. And they said, this is great. We got a significant linear relationship through this. P less than 0.05. Well, here's the fallacy of p-values. That just means that's better than a straight line through this. It doesn't mean it's the best one. Now maybe with this it is there, but frankly, I see the potential for an asymptotic relationship there as well. And actually this is at about half the saturation rate that we saw. Could be largemouth different, they're doing something different, they got a bunch of species they're trying to avoid. I'm not sure. But I don't think I accept this as proof that we don't have to worry about it. I can anecdotally tell you that I've gone through the statewide fisheries database. There's not a whole lot of stuff that's length-based. Some of the river surveys are. I see some signs of the same leveling off here. Okay, so if we're not going to do this, how do we do it? Well, it's actually pretty easy. You've got this National Hydrography database. You've got 127,000 water bodies for New York alone. That means you've got the shoreline perimeter already calculated for the farm pond and the backyard and everything on up. Or you could just go on Google Maps, Google Earth. You've got access on your phone to imagery that the CIA would literally have killed for in the 1970s. Might as well use it. But I would also urge you to consider using area. It's more difficult, that's true. But you can get problems with the regular shorelines. So this is just an example here where you can't get your boat over this. So this shoreline distance doesn't match where you actually sampled. Down in here, you got some coarse woody debris. It can be, it's not always representative, and between lakes, you may have problems with that. It also means that if you use different boats that have different size fields, you can potentially account for that. You can account for other things that would change your field. Conductivity, power output. Area can potentially bring all that in and make all of your surveys more comparable. And I'm going to end here. So Reynolds said, this is really hard. That's the thing I hear most when I say we should be doing this differently, is it's hard. So raise your hand if you've got a wristwatch on right now. Show of hands. Okay. Now raise your hand if you've got one of these with you right now. So in this room alone, there are more GPS devices than there are simple timepieces. I don't think this is true anymore. And I'll rest my case there. Thank you.